In this lab, I want to take a look at analyzing the operation of a solenoid shot bolt. The shot bolt is operated with a electromagnet solenoid, and for this particular example, the solenoid pulls on a lever with a range of motion of about 10 to 12 millimeters, and then that lever then in turn pulls the bolt with a range of about 15 millimeters of motion. As the electromagnet fully energizes, it reaches up to about 30 newtons of force, and then when it's released, or actually when it's still energized and the lock is opened, the return spring compresses and has a force of about 9 newtons. Then when the solenoid is not energized, the lock returns to a locked position, and the magnetic force on the starting magnetic force for the solenoid to re-energize is about 3.3 newtons. Let's just call that 3 newtons. And the spring return force when it's not fully compressed is about 3 newtons. So let's look at setting this up in dynamic simulation and see how we can make some adjustments and make all of this work. Let's take a look at this example of a locking mechanism. So there's a solenoid over here, or electromagnet, that pulls on a lever which causes this plunger to pull back. When we push on this plunger and with the magnetic force, then this locking mechanism opens. Okay, so I've set a home position with it locked, and then when it's energized, it unlocks. I'm going to replace this physical spring with a spring force. So let's go to the model where that physical spring is removed, and then we will go to the dynamic simulation environment. So I'll go into dynamic simulation. I have 3 dynamic simulation joints. I have a prismatic joint for the solenoid, 1 degree of freedom. It translates along the x-axis. I have a revolution joint at the pivot point for this arm and for this lever arm, and so that's 1 degree of freedom, revolves around this axis. And then I have a prismatic joint for this bolt, and so it translates or moves along the z-axis. I've put a sliding cylinder on plane joint between this cylinder and a plane inside of this lever, and it might be a little bit easier to see if I go to a section view. Let's go into a half section view, and first I'll need to turn on some planes so that I have a plane that I can select, and so I'll do a section view of the assembly, and now let's turn off those planes. So I have a sliding cylinder joint up here, and then I have a second sliding cylinder joint here where this pin in the lock slides along that slot. I've added a spring force here to hold this plunger out until the solenoid is energized, and then it will pull that in. I've put a preload on this spring, which we'll talk about in a little bit. I can adjust the preload on the spring by decreasing or increasing the distance from here to here. And of course, in the real mechanism, you would do that by turning this screw. I have a 2D contact to limit the motion, so that when it pulls the armature back, it only goes till it hits a stop. In that direction, then I have another 2D contact so that when the solenoid is energized, it stops when it reaches this face right here. And then I have the force that I have put in for the magnetic coil. And let's look at those. So this force is pulling in this direction. The force for the spring is going to push between this space and this space, so it's going to, the end result, since this is constrained, fixed in space, is it's going to be pushing in this direction. Okay, so the main body is grounded in space, so the force of the spring will push in this direction. So it's going to be opposite from the force of the armature that holds this closed, or the armature out when it's not energized. When the armature is energized, it pulls against it, overcomes that spring force, and brings that armature in. Let's look at that force on the armature. So let's edit that. And what I've done is I've brought in a spline from some physical testing. So I went to a list of points. I imported those points, and that gives us then the curve for that force, depending on how far the armature is pulled into the solenoid. So it starts out a little less than 5 newtons of force, and as I increase the distance that I pull this in, it increases up somewhere, depending on how far I pull this in, over 25 newtons. All right, and we'll look at that in more detail in a minute. I've also put a condition in here that if time is less than or equal to half a second, then that force is applied. Now I can change the amount of time that I want this to remain open. So if I want to give the operator a full second, or 10 seconds, or 20 seconds, or a minute before, or whatever period of time, an hour, a day, before the lock returns to a locked position, I can put in that time right here. But I have it set to half a second, primarily to keep our graph distance short, so that we can easily see what's happening. I will now play this, and we will see it in operation. So I've got it set to run for 3/4 of a second. Remember, at half a second it will release, and it should go back to the lock position. So right now it's in the lock position. It'll go into the open position, and then it'll go back to the lock position. Let's go ahead and play it. Okay, so about 0.1 seconds it has opened fully. At about 0.5, or at 0.5, it should then close the lock. Okay, right there. So now it closes the lock anytime beyond that. Now the first time was just to do the calculations. If I rewind this and play it again, of course it runs faster, but again, that isn't real time. You know, that's the computer calculation time. The real time is 3/4 of a second, 0.75 seconds. Let's open the output grapher and look at some of the parameters that were recorded. And so I'm going to go to the output grapher, and I want to look at the distance that the two prismatic joints. Remember, I have a prismatic joint for the solenoid, and then a prismatic joint for the bolt itself. Turn on the display of the position, and so I have the position of the armature going into the main body. That's the solenoid. And I see that I start out at a position 0, and then it's brought into the main body about 12 millimeters. Actually, if I search on here for search max, I can get a distance, actually 10.6 millimeters. So it's brought in 10.6 millimeters to open the bolt, and then the lock stays open until 0.5 seconds. Notice that it took less than 0.1 second for the lock to open. So if I go back and forth here, we can see that lock opening, and so a little less than 0.1 second for it to fully open. It stays open till 0.5, and we can change that distance, or the amount of time. And then after 0.05 seconds, then the solenoid releases, which causes the bolt to come back out in the locking mechanism. Now let's also look at the distance that bolt has moved. So this graph shows the distance that the solenoid has moved. let's look at the distance that the bolt has moved. Now it's moving in our coordinate system, it's in the opposite direction. I'd like to see the absolute value of this, so let's go ahead and change that. So I'm going to go to that curve properties, and I'm going to multiply -1 times that. Okay, now we have our curves going in the same direction. So now the blue curve is the solenoid translation distance, and then the red curve is the distance that the bolt moves, and so it moves about 15 millimeters to its open position. There are some adjustment nuts here on the solenoids so we can adjust that position by a slight amount. Okay, so we saw how to get an absolute value of that curve so we can compare those two distances, and we achieve that with this lever arm. Let's look at some more parameters, and I think before I do this, well, let's just look around here. Let's look at the force for the solenoid, and so I will go ahead and check that curve and displays it. So the force, we said from the spec sheet somewhere around 3 newtons, and it goes up, in this case with the distance that we moved, it goes up to about 21 newtons. And again, we can search min and search max on this. And we need this spring, the start of that spring, we need to be a little less than the minimum force here in order for the solenoid to overcome the force of the spring. So if I search min on this, and I'm on actually I have 0 force over here, so I need to get over here. So I start out about 3.5 newtons of force that the solenoid is able to energize right at the beginning of its motion, and I need for that force to be slightly more than the amount of force that the spring has going in the opposite direction in order for the solenoid to overcome the spring. So let's look at the spring force, and again my spring force is going in the opposite direction. It would be easier for me to compare the two forces if I have them going in the same direction, so I'll put absolute value on this. So let's go to that curve properties, and I'll multiply that times -1. Okay, so I need the solenoid force to be slightly greater than the spring force, and so that the solenoid can overcome that spring force. And then when the force on the solenoid is de-energized or released, then it drops back down to 0, and then the spring force goes from where it was up here somewhere around 12 newtons. That causes the spring to push the lock closed again, or pull back on this lever, and so then it comes back down. And let's look at that as minimum value on the spring force. I'm going to search min. Now actually it might be max because it's we multiplied it a negative value. So so this one was about 3.5 on the solenoid. That's its beginning force, and about 3.1 or 3.2 on the spring. So the solenoid has to be slightly stronger than the spring at the start in order to overcome that spring, and then stay a little bit greater than the spring as it's energized. From the data sheet, we can see that the magnetic force of the solenoid must be slightly greater than the preload force on the return spring, and so that it can overcome that return spring as we energize the solenoid. Let's look at that in a slightly different way. I'm going to edit the solenoid force, and right now I have this condition turned on. Let's turn off that condition, and remember the condition was to energize the solenoid for a time of half a second. The solenoid actually becomes fully energized, or at about 0.1 second. So I'll turn that off, and so it will stay fully energized. And then let's set our time to 0.1 second, and then I want to look at the force relative, rather than relative to time. I want to look at it relative to the position of the solenoid. And so I'm going to right click on the position of the solenoid, and I'm going to set that as my reference. And so now down here I have the prismatic, or the distance that solenoid has translated or moved on the x-axis. Now let's run it again. Okay, so here is the curve of the force on the solenoid, and here is the curve on the force on the return spring. Now in this case I have used a linear spring, and so the distance that I compress the spring, the amount of force is proportional, linearly proportional to that distance of compression. I could use a nonlinear spring and maybe follow more closely behind this curve, but I always want to be a little bit below the solenoid curve so that the solenoid can in fact overcome this spring. But the stronger that I can make this spring, then if there is any binding in this mechanism, we want to be sure that that spring can overcome that binding and pull the lock closed again. So the closer we can stay to the solenoid curve, the better we are. So I would probably replace this spring with a nonlinear spring that force increases as we compress that spring more and more. Now recall that we have an adjustment screw here on the end of the armature that we can increase or decrease the preload on this spring. And so if we increase the preload, then we can get this line closer to the solenoid curve, but we have to be careful that we don't pass over that curve. Or conversely, if we found that our solenoid wasn't opening, and then we need to reduce this force on the preload spring or the return spring, then we could reduce that by the adjustment screw here. So let's take a look at doing that. So I'm going to go to the armature, and so here is my screw that adjusts this part right here that adjusts the preload on the spring, and I've given that relationship a name. I've called that spring preload, and right now I have it set on 1.5 millimeter offset distance between here and here. So I could try it at 0. If I want to increase the preload, I could try it at, if I need to decrease the preload, I could increase that distance. And our spring itself is 20 millimeters long in its free state. And so then when we put it into the mechanism, when we put this spring into the mechanism, it's actually about 17 millimeters from here to here. So we have about a little less than 3 millimeters preload on that spring. And the spring itself is rated at 1 Newton per millimeter. So, and 20 millimeters is its free length. It's compressed not quite 3 millimeters, so it's a little less than 3 millimeters in its preload state. And remember that the solenoid energizes at just over 3 newtons, so we need this spring preload to be just slightly less than the solenoid. I'll say okay to that. Then let's adjust that preload, and I can go either way. Let's edit that, and I'm going to change that distance to 1.25. So I decrease the distance between here and here, which increases the preload. I've compressed the spring by just a bit. So let's go ahead and save that, and I'll go back to the assembly, and let's turn our output grapher on. And again, as I play it, I want this blue curve to stay below this magenta curve. And so let's play it again. And the two forces act together with each other. So we've got a force on the solenoid going this way and a force on the spring going that way. They're going the opposite direction, and it would be very difficult to hand calculate the interaction between these two forces, particularly because this one, is easier because it is a linear spring, but the solenoid isn't linear, the force isn't linear. And as suggested, I might put a nonlinear spring in here to try to more closely follow that curve. So the mathematics for that become very, very complex. where we can do some quick trial and error substitutions and then specify our spring that we want here. We know what the specs are from testing for the solenoid, and then we can adjust the spring that we need to get our return, so that this mechanism operates even as it becomes dirty or is under less than ideal conditions. We want it to be reliable. Now I might want to analyze how the forces interact with these other parts. Let's look at then, I have a sliding cylinder to this lever here and a sliding cylinder to this end of the lever. Let's look at those forces. So I'm going to clear the graph, and I'll go to the sliding cylinder joints, and I'll turn on the force, the curves for the forces on those two joints. Then I see the red curve, the force is slightly higher, so, well, actually both of them are their high points up here. So I'm going to search max on that, and I'm going to put a time step then on, I'll put a check mark here on that time step, and the direction of the force is going in one direction here, and then it's going in a different direction over here on the other side. So I'm going to come back here to the beginning, and I might want to put a time step, check a time step on that, so I can see as those forces change direction, how do they interact with that part. And then I will export that part to FEA, and so I will go ahead and select this part, and then I need to tell it where the force of the revolution joint is on that face. I'll say OK to that, and now I can go into the FEA environment to analyze this part. So I'll rewind, I'll go back in construction, and I'll save it. I'll go to my environments, and I will run a stress analysis, and let's tell it to create a new study, and I'm going to do a motion loads analysis. And so I have two time steps that I have saved, one with the maximum force in one direction and the other with the maximum force in the one for the opening and one for the closing. And so let's go ahead and look at this one. This one was the higher forces, and I will say OK to that. Okay, so we have these various forces that were applied, including some twisting forces that we might not be aware of if we were just doing some hand calculations, pushing against this and pushing against that face. We might not be aware of these twisting forces. Let's decrease the size of those glyphs a little bit so that it looks more appropriate for our model, and then we'll run our simulation on that part. And I might want to leave the section visibility while I'm doing this so we can see the entire part, and then we will go ahead and run the simulation. And on our initial run, okay, keep in mind that we're looking at an adjusted representation so that we can more easily see the results. I'm going to put that on actual, and so let's look at our safety factor first. Our safety factor is beyond 15. If I want to look at our displacement, then our displacement on this part is 10 to the negative 5 millimeters. So that's a really a tiny number. So maybe we could experiment with reducing the weight on this part or the mass by removing some of the material. We can see that it's way over engineered for the purpose that we need for it to perform.